let me talk some more about these notations. So that's, the notation is not just writing it, but it has a lot more into just that. So here's the thing. There's a term in calculus here that's called differentiate. And it's a very special terminology that's starting from now on, you will hear me to say that a lot. Differentiate. So it's a term, it's a verb, but what does that mean here? It means the same as take, right? Or in many other instances, we find, right? We take, we find the derivative. Okay. So differentiating means that process of finding the derivative, or just for short as a verb, right? Differentiate the function f of x. It means we find the derivative of that function f of x, and then differentiate whatever else, right? See what I'm saying now? But see, because being a verb right there, being an operation right there, right? Here's how it come out with the symbol. So it goes way beyond the notation. The notation we have here has a lot of meaning. See, so when you say you differentiate, and now it's where I'm starting to say that I favor the use of this dy dx thing right here. Because you see, when your equation is y equals some function f of x, right? The idea now is that this symbol d over dx, just that symbol means we differentiate. Just when you see this symbol, it means differentiate. Okay. Differentiate. We take the derivative. Take the derivative of what? Take the derivative of the function y. See what I'm saying now? Okay. So I put it in the order. See, it started out with this notation. That notation means differentiate. It indicates that, hey, take the derivative. Take the derivative of what? Take the derivative of y. Originally and classically speaking, we got to put parentheses around, meaning we apply this notation, we apply this work, we apply this operation to the function y. Am I making sense? Okay. And then the same way we can alternatively, you see the prime right here. The prime right here means on your function f, right? Differentiating, we apply the prime to that as well, right? That's another symbol for us. So the prime symbol, it also means differentiate. So two different ways of using that. Okay. And so I prefer this symbol better because see the dx in the denominator indicating that hey, our objective is to find the derivative of the function y, okay? But then the x here is making it more clear that this is the main variable. Okay? The main variable of your function f of x. You know what I'm saying? Or now it's precisely speaking, differentiate in respect to x. Okay? Sorry for a little bit of a theoretical and kind of like a language-based kind of thing right here, but it will drive into I'll understand later. So the dx in the denominator is indicating that hey, the function here, we're taking x as the main variable, as the variable that we're taking. And so now when we get through with some of that understanding about the notations, derivative rules that I'm about to say right here, just the power rules itself that we have just discovered not too long ago, right? The first thing to remember, we have already discovered the power rule. So the short form of that, see, I don't like writing, hey, if f of x equals x to the n power, then f prime of x equals whatever, etc., etc. So here's a short form for you. X to the n is a power function, right? See, differentiating that. See how I apply that notation right there? See, I apply the dx directly into the function. Okay? Differentiating the function x to the n, any function x to the n, will come out with the derivative, right? Equals n times x to the n minus 1. You see how quick and convenient that is once you understand the use of notation? Instead of saying, hey, if the function is x to the n, right, then the derivative is going to be n times x to the n minus 1. That's way too long. We just simply write it down. d dx, right, on the power function equals n times x to the n. Differentiating that x to the n power, right, will come out with this answer, n times x to the n. Make sense? Or it's even faster. It's even faster to use this. Sometimes, but faster may lose a couple of some of the meaning here. But you can also use a prime symbol. See, differentiating the x to the n function, right? The answer will come out being n times x to the n minus 1. So it's sort of like now become a formula. So this formula, yes, students tend to like that a lot more, okay? But it's already cut short some meaning, right? Some other detail like that. But of course, admittedly, when instructors are writing down different derivative rules later on, I have to keep sticking with this. But personally speaking, I prefer using this notation better. And so now the power rules is kind of like being revised into the shorter form. All right, so now I'm going to keep swinging back to this board here for further rules, and we're adding it. But now let me start out with another example here, and right after the example, we're going to discover some new rules. For this example, because we depend on the problem to, let's call it a demonstration problem, number 1 right here. That we have to come up with a problem, and then from that problem, it leads to learning a new rule right here. So, how about I'm going to start out with a function like this. F of x equals, pick me a number, please. 3. Thank you. F of x equals 3. Okay. And we want to find prime of x. See if we want to differentiate, right, this function again in respect to x and find the derivative of x. And instead of calling that an example, it's simply because an example, in my understanding, it's more like where we apply what we have already learned. But here, it's a one problem that started out and that lead us into learning the new stuff. Okay? So that's why I have to call it. It's a problem that was promoted. But here's the thing: what kind of function is this? Yes.
It's a constant.
It's a constant function, right? Because simply if you input x equals 5, the function comes out with output 3. You input x equals 1,000, the function comes out with output 3. You input a negative number, right? The function will come out with output 3 again. That's why it's a constant function, right? Good. But now I want to find f prime of x here. So we only learned a power function, right? But this function is not a power function. It's a constant function. So guess what? You cannot use the power rule we have derived earlier into this. See what I'm saying? That. Okay. So now, why do we do this? We have to roll back. See, from now on to the rest of the quarter, you have to understand we're gonna learn a whole bunch of derivative rules. But then, when you're working with some function that stays outside of where you can apply those derivative rules, we have to roll back to the limit definition. Am I making sense? There will be a lot of instances where, hey, you learn the rules. Good, lovely rules, right? It works so many times, but then all of a sudden you will step into some function that stay out of those rules where the rules are not applicable. At those points, at those instances, we have to roll back to the limit definition, find the limits and all that. And so obviously right here, we learned the power rule, but this function doesn't apply. So we have to roll back to f of x plus h minus f of x, right? We're dividing that by h. You guys see what I'm saying with that? That's how we're finding any derivative as a start. At the starting point, take the limit as h goes to 0. Sounds good? Right? But then for this function, well, I think we go a lot simpler than you think like that. Well, it's a constant function. So independent with x plus h or whatsoever input, f of x plus h will come out output 3, right? F of x will come out output 3, right? And then we divide it by h, okay? And we take the limits as h goes to 0. Right? So that's the setup for our function like that. So let's do that famous difference quotient. We apply that right into our function being a constant function. See what I'm saying now? And then what will this thing be? Remember, we don't directly substitute the h equals 0 in there, okay? We do the algebra first, right? So 3 minus 3 give me 0 over h, right? The limits, it's h to 0. And so that means what? It's just 0. You guys agree? Because think about it. Before h can get close enough to 0, this quotient has already been 0. That's why the answer is coming out 0. Sounds good then? So I fired up a limit process again, but my target is we found that derivative. So if you recognize here, what happened if what happened if it was f of x equals 10 right here? Because he volunteered for me f of x equals 3, right? And I use that as our constant function. What happened if he gave me f of x equals 10? Would that change this result? No, because it's going to be still 10 minus 10, right? Come out with a 0. What happened if he gave me at the beginning the f of x equals negative 1,000? It's still not going to change the answer, right? It's still negative 1,000 minus negative 1,000, right? And it come out with a derivative 0. See what I'm saying now? So now you guys recognize something? What happens when we differentiate or take the derivative of a generally constant function? You see how I'm writing that right there? A constant function is, a lot of times it's written simply as a c, right? Completely independent with any variable. But then, so, see, the variable indicated is the x. But the x here is nowhere involved with your function, right? That's what I'm talking about right there. I favor using this notation in that sense. It indicates, hey, we differentiate that function. But the variable here is the x variable. It has nothing to do with this function. So in the way I'm seeing it, it has to be a constant here, right? But in the end, when we take derivative or differentiate a constant function, what do we have as a result? 0. See that? Okay, so now we put into our list. We put into our list right here. Yes, differentiating a constant function, right, in respect to x. Yes, the answer will come out to simply a 0. And even a shorter term for that, a shorter form for that constant term, take the prime of that, right? Come out 0. There you go. And we call this is rule number 1 right here. It's sort of like the very first rule, taking the derivative of a constant function. Everybody now will know, right? That taking the derivative of a constant function, we would simply give you a 0. No one can argue about that. So now, as far as the derivative rules, yes, you got the power rule on top of that, right? Specifically work out for the power function. And then now, this rule here is the beginning of some what I so-called a universal rule over here. So, universal derivative rules. Okay? Because that rule right here is specifically working on when you have a function that's specifically in the power form. Okay? But then this rule that we have just found out here, it works anywhere as long as you, anytime that you see a constant term or a constant function, derivative come out is simply 0. Okay? And then now another universal rule here that here allow me to just tell you guys. Okay? And then one day when any one of you have a good passion for math and decide to go on to a much more advanced course in calculus, the same stuff here, there, they will make you prove these rules that I'm showing you today. Okay? But think about a lot of times your function comes with 2 terms or multiple terms, like an f of x and a g of x, either be added or subtracted from each other. Okay? Multiple terms. So now, differentiating this. See, so now for convenience and to save your time writing, I switch over to use a prime symbol over here. But differentiating a function with multiple terms, this rule allows you to differentiate 2 separate terms here. Okay. Differentiate f, differentiate g, and then add or subtract, depending on how it was in the beginning. Okay, so we have a rule that. So this rule basically tells you that now you can take the derivative term by term in your function. When your function got multiple terms, right, you can just find the derivative individually on each term and then add or subtract them. And then the third universal rule over here, when your function has a coefficient in front of that, right? Taking the derivative of something like this, or differentiating something like that, you can just do that as easily as take the derivative or differentiate f of x, right? And then multiply that with the constant c, with the coefficient c. Right? And so let me tell you, with just those 3 universal rules together with this power rule we've learned previously, it's enough to kick all day with derivatives. Right? So this new topic right here that we're starting to get into some rules of taking derivative. Let me start the example number. So all I'm asking, find the derivative, right? How about our first function? And along the example right here, allow me to show you how I use the notation. Part A, how about we have a f of x, right, equals 4x to the 10th minus 20x squared plus 5. All right. So before we get into it, let's just have some quick observation of the function before we move on. Right? This function here, the one big thing, it got multiple terms, right? It got 3 terms. The first term is a 4x to the 10th, right? The next one is a 20x squared, right? The next term is a constant term 5, right? So at least what rang the bell already is that we have this rule number 2 that allows us eventually to work on the first term, the second term, and the third term separately, right? See what I'm saying now? All right. And further, I realized that each term here, now think about it, when you're at that step where you're working individually on each of these right here, it's got powers and powers, right? And then it's got coefficient in front of your function. You see what I'm pointing out? And so now, here's how we get into the action right here. So f prime of x, right? Yes, we're starting out by doing this. 4x to the 10 minus 20x squared plus 5. Taking the derivative means you take the derivative of the whole thing here. But that's rule number 2 here. The rule that we can take derivative term by term allows you to do a separate derivative for this. Right? And then between these 2 terms is a subtraction, right? So you can subtract a separate derivative for 20x squared. You guys would read that? Right? And then between these 2 last terms right here was an addition, right? You can add the separate derivative for that constant 5. So I used the derivative rule just now, right? That, hey, I can find the derivative term by term. In the next step, see that one right here is a coefficient multiplied with a power function, right? Let's write it down. It means we are allowed to just find the derivative of the 10th power, right? And then multiply with a coefficient at the end. And then for that term right here, it's the same way. It's a power 2 on the x, right? X to a power with a coefficient. That means derivative rule number 3 allows me to just find the derivative on the x squared term, right? And multiply with 20. See what I'm doing there? And then the last term right here, now you can tell me the answer. What's the derivative of the constant right here? It's a 0. See what I mean? Right. And so now in my next step, think about it. What's the derivative on the x to the 10th power? The power rule that we've just learned, right? X to the 10th power, yes.
And 10x to the 9th.
That's right. 10x to the 9th, that's right. So that's the derivative of the 10th power. And now we multiply that with 4 in front with that coefficient. Minus, see, 20 multiplied with, what is the derivative of the x squared right here that we have found? Anyone? Yes?
That would be 2x.
There you go. Okay. And the last term is a 0, so there's no need to write it down, right? And so now, what do we do next? And by the way, at this point, we have already found the derivative, right? It's just a matter of sort of like rewriting these to make it look cleaner, that's all. So 4 times 10, 40x to the 9. See what I'm saying now? Okay. Minus 20 times 2, 40x. Yeah. We're done. Yeah. That's how we're working with those derivatives. And so here I'm leading through the examples and I show a lot of explanation. That's why it took me so many steps. But you are allowed to just skip from one big step down to that. See what I'm saying now? Because it's still in the end multiple terms, right? And that is a combination of what you're doing a lot of steps. So here you took the derivative of the 10th power, that led it down to 10x to the 9th and multiply with the 40 to make it quick. See what I'm saying now? Okay. So yes, you are allowed to skip your steps like that. All right, let's look at another problem, shall we? So it's all about the plan of how we get it work. Yeah. Let me show you how powerful those rules are learned. Maybe how about y equals, right? Square root of x minus 1 over x plus the 40 over x to the 4th power. So here's how I'm seeing it. Yes, the plan is to eventually use because the rules we've learned so far is derivative of the constants, right? Derivative for term by term, the derivative for the coefficient, the derivative for the power. Do we see any of that here? But we got the we can take the derivative term by term. But then how about when we get to that, taking the derivative of the square root? Do we have a rule for that? I don't think we have a rule for that, right? And then the derivative of the 1 over x right here, we didn't have a rule for that. And then the derivative of the 40 over x to the fourth, we don't have a rule for that. Right? But here's the word. Algebraically, I'm just talking about before taking the derivative. Okay? Algebraically, square root of x is understood famously as x to the 1/2 power. You see the power again. You know, do that. Okay? The 1 over x here can algebraically be understood as a power negative 1 of x. Okay? So I never said from the beginning that the power rule that we use has to stick with integer power or have to stick with the positive power only. It applies to negative power. It applies to rational powers as well. Okay? And so the last term here, the 40 over x to the fourth, think of that as a 40 coefficient. See, right here, it's a 40 as a coefficient multiplied with 1 over x to the fourth. Did I give you a hint? Think of that one like that, right? So now it means 40 times x to the negative 4 power. See what I'm doing now. Right? So here's what's starting with this problem. Let me show you how you can skip step here. Yes, your function goes y equals, right? Y equals. So we stick with the symbol dy dx because x is the main variable, y is the function. But now, first term, coefficient 1, right? The derivative says what? We multiply the 1/2 down, x to the 1/2 minus 1. See what I'm doing there? So we get right to the derivative already. And the coefficient is just nothing but other than 1, right? I highly recommend to write down the subtract 1 like that so that it make it clear on the calculation of the final power. And then the next term, yes, minus, right? The negative 1 multiplied down, negative 1 x to the negative 1 minus 1, original power minus 1. And the last term here, 40, coefficient, right? The derivative on the x to the negative 4 gives me minus 4, right? Times x to the negative 4 minus 1 again. All right, so now we can, the answer here comes out dy dx in the next step right here. See? 1/2, what's x? I mean, what's 1/2 minus 1? Negative 1/2, right? So 1/2 times x to the negative 1/2. You got that, right? Now, negative multiplied with a negative plus x to the negative 2, right? Negative 1 minus 1, that's negative 2. That's the part where you got to be cautious sometimes. A lot of times people give me negative 1, right? They took it down and they think it's become a power 0 here. They think about as a magnitude 1 minus 1 right there, but it's a negative 1 minus 1. Right? And now the next one here is a minus, because 40 times the negative 4, right? Minus 160. Right? X to the negative 5. So as far as finding the derivative, you are done right here. Right? You could have written this one here in the algebraic equivalent forms. Algebraically equivalent form that's 1 over the first term here is 1 over 2 square root of x, because the negative 1/2 power is a square root, right, in the denominator, plus 1 over x squared minus 160 over x to the 5th. Be ready to write your original derivative into this form right here, because some assignment problems may ask for, hey, write your final answer in a way that's without negative powers. Without negative power, that's how you're writing it. You know what I'm saying that? Okay. Third one in this example. Our function is g of x equals x to the 5th times square root of x, right? Plus 5 times the 5th root of x. Power rules and those universal rules that allows you to work term by term, those are the only rules we've learned so far. But trust me, we can do a lot so far. So here's how I'm seeing this. This is x to the 5th in product with the square root of x, right? So think about it this way. Just that term separately on its own here. Allow me to explain this. X to the 5th, yes, x to the 5th, times, how about we rewrite that as a power 1/2? You guys remember that? Remember from the previous problem, right? Now the power 1/2, think about it, same base, and when we multiply the two powers of the same base, what do we do with them? It's the power of 5 plus 1/2. Remember that from algebra right there? What's 5 plus 1/2 as one overall final power?
5.
Okay, 5.5, we have a fraction. 11 over 2, there you go. Let's get more used to communicating with fraction. See what I mean? Okay. So, that means what? The first term here, and I'm not doing the derivative yet, I'm only re-expressing it algebraically. First term, x to the 5th times the square root of x. It looks completely complicated at first, but now we realize it's just simply x to the power 11 over 2. So you guys will need that. And then the next one is the coefficient 5, and I can rewrite that x to the 5th root as x to the 1/5 power, similar to the square root problem that we've done earlier, right? So now we display, so every term now is displayed as a power function. You see the routine that we've been doing so far? Because we only learned about the power rules, right? And so every problem here, in every term in our problem, we express that as a power of x. We express it as a power of x. And maybe with some coefficient, right? And then once we got past that point, right, then everything else will be easy. G of x, I mean G prime of x, right? See, now it's 11 over 2 multiplied down in front, right? And we have the power becomes 11 over 2 minus 1. Please, for starters, write it down like that. Plus, then you got 5 as a coefficient, multiply with the 1/5, multiply down from the original power, and then multiply with x to the now 1/5 minus 1. You guys repeat that? Okay? So now go ahead and do your calculation. So 11 over 2 minus 1 is making it what? So it's going to be g prime of x, right? Be just 11 over 2 times x to the 9/2 power. So that's 11 over 2 minus 1 plus, and in my next term, 5 cancel with 1/5, right? Giving it just 1. So x to the 1/5 minus 1 is a negative 4/5. You guys agree? Right? We're done with that derivative. Right? That's how we get it. All right, so we're going to continue working with some more derivative rules. I need some more examples here. So after we're doing example 1, let's get ourselves in example 2. I want to introduce some more props for you guys to look at. So we just want to, it's very similar instruction with the earlier example. So we want to find the derivative f prime of x using that symbol if our function is in the functional notation, or we can use the dy dx. And these both means derivative. I just want to get you guys comfortable with both ways of writing it. So how about our function here in part A? We got the 4th power. So spend some time writing it down. Okay. All right. So at this point, remind yourself that we have only learned about a few 3 universal rules, right? The rule for taking the derivative of a constant, the rule that allows us to take the derivative term by term, right? And then the rule for taking the derivative when the function has a coefficient in front. And then aside from that, we got the one specific rule being the power rule. But then this function here is not in any of those. This function falls completely outside of those categories. So think about when we still learn, when we have learned only a very limited understanding here, and we're asked to do something that seems like beyond our capability. And here's the algebra can once again comes back in and helps a lot into the problem here. So I'm talking about before we're doing the derivative. Think about this function here from start, right? It's a rational expression, right? It's a rational function right here. One numerator, and then the one single term denominator, and then the numerator here has 2 terms, right? So now I can go ahead and, so it's just the algebra work. Before taking the derivative, I'm going to rewrite it as a 2x cubed over x to the 4th. See what I'm saying now? Okay, algebraically we're allowed to do that, right? And then subtract 6 over x to the 4th. So now that term here specifically, start bringing back some memory from our earlier example. See what I'm saying now? Right? And then so, you can also see the 2x cubed over x to the 4th. Now we can nicely cancel the x cubed with the x to the 4th, but here making it 2 over x. We get and minus 6 over x to the 4th. And so now all of a sudden, our rewritten form of the function right here will work because we can turn that into the power forms. So 2 over x right here, we can rewrite it as x to the negative 1 power, right? Similar to some of the problem we have done in the example 1. And then this next term here is a minus 6 times x to the negative 4. See how the algebra can help a lot sometimes like that? So from something that was looking completely unfamiliar to us, but using some algebra, we were able to bring it down to the level that we're familiar with working with that. And so now we're ready to take the derivative term by term, right? Where each term here has a coefficient and a power. Coefficient and a power. So the point is try, within these days when we only learn a very limited amount of rules right here, right? And we specifically, that special rule is the power rule, and just simply try to turn your function into power forms like that, into multiple terms with powers of x, so that we can apply the power rule. So that's the idea and the intention of the example here. So now, f prime of x, right? Our function was written as in functional format right here, so it's better that we use the f prime symbol here. So now I'm going with 2, right? The power multiplies down, giving it 2 times negative 1, right? And x to the, I highly recommend to write it negative 1 minus 1. Right? And then subtract 6, and then the power negative 4 here, I'm going to multiply down for that term. Minus 4, right, times x to the negative 4 minus 1. Okay. So every original power, we're going to subtract by 1, right, using the power rule. And so in that case, our final answer comes out being, this term here becomes a minus 2x to the negative 1 minus 2 power. And then minus term right here, but with the negative sign here, we're turning that into a plus, right? Plus 24x to the negative 5 power. So technically, at this point, we're done with our answer in terms of finding the derivative. Okay. But then be completely aware, that there could be times, there could be instances where you are asked to write your final derivative that's free from the negative powers like that, right? And in that case, you can write it as minus 2 over x squared plus 24 over x to the 5th. Yeah. So I'm talking about just, in case that you're required to put your final answer free from the negative powers, right? And this is how we're rewriting it. Okay, but these two answers are the equivalent expressions. So that's one more problem right here that introduces the use of the power rules, but we have to use that a little more creatively. Okay, so how about let me bring in another problem with that. So how about in part B right here we have y equals, right? That's a b product. X, 2x minus 3, then x squared plus 5. Right? So go ahead and spend some time writing that down. And yes, it's another function where we're asked to find a derivative. So with this function, once again, we have a product between two separate polynomials, but we haven't learned any rule that directly handle the product like this, right? So the best that we can do right now, and remember, keep in mind, the only rule we've learned is the product rule. So we are going to try our best. We're going to try our best to display the function here as multiple terms where each term is a power of x. Okay? That's all we can do right now, right? But of course, that's what we can do still. So I'm going to FOIL out, just like that. So now this is the algebra step before we take the derivative. So 2x times x squared right there gives me a 2x cubed, right? And then 2x times 5 right there gives me a plus 10x, right? And 3x times x squared right there minus 3x, right? And that gives me minus 3x squared, right? Minus a 15. You guys all agree? Right? And then we can rearrange the terms here to make it a little nicer. So 2x cubed minus 3x squared, right? Plus 10x, right? And minus 15. That's our same function, right? But in the expanded form right there. We have to FOIL it. All right, so now we have successfully displayed out, we have re-expressed our function where it contains just multiple terms, right? With all just powers of x with some coefficient. So now we bring ourselves back down to that level where we can apply the power rules mixed with the other universal rules. Okay. So now the derivative steps officially kicks in here. And we go with the y dx symbol again, right? So first term here, power rule says you can multiply the 3 down, right? Together with the coefficient here, it's making it, so let's write it like this. The coefficient multiplied with 3x squared. Are we good with that? Right. And then the next term minus the coefficient is a 3, we multiply that power down, making it 2x, right? And the power here is easy enough. That you can see it's just power 1, right? It's 2 minus 1. The next term here is a 10 for the coefficient. We probably have not done anything like this, but this is power 1. You see what I'm saying? Now, when you don't see that power, it's power 1, right? So power rule applies again. It means when you break down the power, it's just going to be x to the 0 power. Now, see what I'm saying? No? Multiplying the 1 down, we don't need to write it, right? And then the power here becomes the 0 power, and then minus 0, right? The derivative on the constant term here is 0. You guys are all following with that still? And so now let's clean up the terms a little bit. First term is going to be a 6x squared, agree? Middle term here is going to give me a minus 6x. What's x to the 0? It's 1, right? So 10 times 1 right here. So plus 10. So yes, I agree. This x equals to the power 0 equals 1. The algebra. And then there's no need to write the minus 0, right? So you're done with your derivative here. And this derivative is quite final in the sense that it already has all of the positive powers and all of that, right? So there wouldn't be any instance where you were asked to write it without a negative power. It's already all positive power.